Hi all, welcome back. It's Professor Marinos, and today we're going to begin our module on kinetics. So up until now, we've mostly been considering equilibrium phenomena, or the state of a chemical system once that chemical system comes to rest, when reactions are no longer proceeding either in a forward or reverse direction. But as the Greek philosopher Heraclitus said, all is flux, nothing stands still, and that is definitely true of environmental chemical systems. In environmental chemical systems, we actually only rarely truly achieve the state of equilibrium. And so while equilibrium is a useful guidepost to telling us what reactions can occur versus cannot occur in a system, the actual rate of these changes as the system proceeds towards equilibrium is not something we've discussed up until now. And that's the domain of kinetics. Kinetics is the science of how fast reactions proceed and how a chemical system will evolve through time. So that's the topic of this module, and we'll get right into it. By the conclusion of this module, I would like you to be able to describe the law of mass action and the rate equations that arrive from the law of mass action. That's going to be the topic of today's lecture. Use analytical and numerical methods to model the evolution through time of a simple multi-step chemical reaction, and also apply the Arrhenius equation to predict how reaction rates change at different temperatures. And by the end of this video, like I said, we're going to cover the law of mass action, and so I want you to be able to write differential equations for any chemical reaction based on the law of mass action. And then we're going to describe also the linkage between kinetics and equilibrium chemistry, and I want you to be able to describe how equilibrium chemistry can be defined in kinetic terms. Okay, so let's get into that. So the foundational law of chemical kinetics is the law of mass action. And this is actually surprisingly easy to state. This states that a chemical reaction rate at any given instant, so an instantaneous reaction rate, is proportional to the product of the activities of the reactants. So you just take the activities of the reactants, or their concentrations in aqueous solution, their molar concentrations, and you multiply them all together, or you take their product, and this product is proportional to the instantaneous rate. So this product multiplied by some constant of proportionality is equal to the rate of reaction that's occurring in that system at that instant. So why is this? Let's make use of a non-chemical analogy to explore the mechanics kind of behind this for a second. So say we have a set of red dots here. These red dots can represent anything you like. And say we're going to check on these red dots at 4 different times. And between different time points that we check on them, each dot has a 1/2 chance of turning from red to green. So we start off with 24 red dots at time 0. And at time 1, you would expect, since each of these has a 1/2 chance of changing to green, at time 1 you would expect for 12 of the dots to have turned green and 12 to remain red. And so the change between time 1 and time 2 was 12. And this is equal to 1/2 times the total number of red dots that you have here. Now consider going from time 1 to time 2. Now we have 12 red dots, and we expect half of them to turn green. And so at time 2, the change will be 6. 6 new green dots have been produced between time 1 and time 2. So the rate of change is 6 dots per time interval here, 12 dots per time interval here, but at all times you're maintaining this constant of proportionality of 1/2. We have a 1/2 chance of the red dots changing to green. So continuing this along, at time 3, you have 6 red dots at time 2, change half of them to green, and so you have a change of 3 green dots over this time interval. And so you can see here, you can just express the relationship, the change in the number of red dots per interval of time, so the total change per total time interval, big deltas, is equal to negative, because you're losing red dots, 1/2 the total number of red dots. It's just a pretty simple expression to wrap your mind around. And then we can call 1/2 our proportionality constant, which we also call K, and just define this as delta red dots over delta time equals negative k times the number of red dots. Okay, so now let's consider this reaction A yields B, an actual chemical reaction. And if we go from this discrete analogy that we made previously to a continuous analogy, we can now just say that the change in A with respect to a change in time, where this is an infinitesimally small change and this is also an infinitesimally small change, is simply equal to negative k, so some proportionality constant, and it's negative because A is decreasing as the reaction progresses, multiplied by the concentration of A. So this is the product of your reactants, all the reactants multiplied together. We only have one reactant here, A, and so the product of it is simply A, multiplied by some proportionality constant, negative k. So this is the law of mass action expressed as a differential equation. The change in A with respect to time is equal to some proportionality constant multiplied by the product of the reactants. Now, you can see that even though this is a constant proportion here, because A is decreasing as the reaction progresses, so A is shown as this orange line here, and as the reaction progresses, you end up with progressively less and less A. Because this is getting lesser and lesser, your reaction rate is similarly decreasing as the reaction progresses. So you start off with a very fast reaction rate. This amount dA dt is very high at first because you have a lot of A over here. But as the reaction progresses and the concentration of A decreases, so too does your reaction rate. As A becomes less and less and less, your reaction rate slows down until by the end of the reaction you have almost no reaction occurring because all of the A is being consumed and it's all being converted to the product B shown in this blue line here. So although this is there is a constant of proportionality to A that determines the rate, because A is always decreasing and because A is changing over time, the rate is always changing over time. The rate is decreasing. So now we've considered this with respect to a reaction with a single reactant, A up here. Now let's consider an analogy of what a multi-chemical reaction, such as A plus B yields C, might look like. Okay, so here's my somewhat tortured analogy for what's happening in multi-reactant reactions, when that is the molecular square dance that we see going on here. So say that each of these dots, different colors, represents a different kind of dancer. And the red dots are the square dance instructors, fancy-footed people who can really make things happen on the square dance floor. And say that every square dance instructor gets paired off with a different dancer for a single dance. And also you can say that perhaps if a square dance instructor, a red dot, gets paired with a blue dot, there's a 50% chance that they both turn purple. Hopefully not from, lack of oxygen, but who knows why. This is a tortured analogy, I told you. How does the number of red dots, or the number of square dance instructors, change throughout time? Well, we can represent this again as an equation. The change in red dots with respect to a discrete change in time, so say this time unit is one dance, is equal to our probability, 50%, or 1/2, multiplied by the number of red dots that exist in our molecular dance. So just as in the last example of the single reaction, we're multiplying our proportionality constant multiplied by the number of potential reactants. And then multiply this by the probability that one of these red dots is going to get paired with a blue dot and potentially cause this reaction. And so that probability is simply the number of blue dots over the total number of different colored dots that exist at the dance. So this is just, this is just a probability, but this can also be thought of as the concentration of blue dots. This is the concentration of blue dots out of the total pool of dancers that can be paired with a square dance instructor. And so you can see that we've multiplied the number of square dance instructors multiplied by the concentration of blue dots multiplied by our proportionality constant, and this gives us our discrete rate of change. Now again, moving this to a continuous analogy from a discrete rate of change to a continuous rate of change, so dA dt, we can simply say that this is equal to our proportionality constant multiplied by the concentration of A multiplied by the concentration of B. So again, this is a mass action expression. We have the product here of our reactants, A times B, that's our product, multiplied by a proportionality constant, negative K, and this equals our rate of change. And you can see here again, so I've, in this example over here, I've set the concentrations of A and B, the red and the green lines respectively, unequal to each other, but their product still determines the reaction rate. So again, when you have a lot of A and B at the beginning of the reaction, the rate is very high, but then it drops off rather precipitously, and this is because you're running out of B. B is the limiting reagent in the system. And so as B starts to approach zero, the mass action expression up here also starts to approach zero, and so the rate gets very, very slow very quickly. So eventually, you can see here, A stays at some constant concentration by the end of the reaction because B is the limiting reagent, and so as B goes to zero, A goes to some constant concentration, but the overall reaction rate, shown here in this black line, tends to zero. So this is just an example of a mass action expression for a reaction that has two reactants, A and B. And it doesn't matter what A and B are, as long as your reaction can fit this form, you can find a proportionality constant that makes this rate law hold.
Okay, I just want to step back for a second and consider the original reaction that we started off with. The reaction was A yields B. And this is a one-way reaction, A yields B. But we know that, in theory at least, all chemical reactions are reversible. So just as A can yield B, B can also yield A. And so I want to consider both of these reactions in turn. So let's write out the forward case. And the reverse case. Okay, so we already developed the kinetic expression for the rate of change in A with respect to time. And we said that this was negative some proportionality constant multiplied by the concentration of A. And just to keep things straight, let's call this dA sub F and K sub F for the forward reaction. Now, can we develop a expression for dA dt with respect to the reverse reaction? Well, yes, we can. So let's call this dA sub R. Well, the change in A is equal to just the negative change in B. And so we can just drop this negative here and just say some proportionality constant times the concentration of B is equal to A. B is the reactant, so B ends up there. And the change in A is just equal to the negative change in B. Okay, and then if we consider both these reactions together again, so now considering both of these together, we can say dA total with respect to time is equal to the forward reaction rate plus the reverse reaction rate. Okay, so that's nice. What can we do with this, though? Well, I want you to consider for a second the case where this expression equals 0. So the total change in A with respect to time equals 0. And let's just sub in these expressions for dA forward with respect to time and dA reverse with respect to time. So we end up with 0 equals negative K forward, this is lowercase k, multiplied by A, plus the reverse reaction constant multiplied by the concentration of B. Let's just do a little algebraic rearranging on this, and we can say, we can move Kf times A over to the other side, and divide through by k reverse. And then we would move the a to the other side as well. So we end up with b divided by a. And so that we can see that when the total reaction rate equals 0, the concentrations of B and A are in the same ratio as the concentrations of the forward reaction constant divided by the reverse reaction constant. Now, this is all well and good, but what does this mean? Well, consider this 0 here. What exactly does it mean to say that the change in the total amount of product or reactant is equal to 0 with respect to time? The only time when there's no reaction ever occurring in a system is when that system is at equilibrium. And so this is a pretty profound and beautiful thing that might give you pause when you look at this. What's this now? This is now B at equilibrium. This is now A at equilibrium. And this, the products over the reactants, is big K, your equilibrium constant. And so we've just demonstrated through this a very profound link between the kinetics of chemistry and the equilibrium state of chemistry. So when you're at equilibrium, your reaction quotient, your products over your reactants, raised to their stoichiometric coefficients, of course, is equal to the reaction rate constant of your forward reaction divided by your reaction rate constant of your reverse reaction. So this shows a very nice link between the domains of kinetics, and big K is your big K from equilibrium. Equilibrium chemistry. And note, you can't deduce from your equilibrium state what your K is going to be. Equilibrium doesn't tell you anything about the rates that happen, or at least it won't tell you exactly what those rates are, but it does say something about the ratio of the rates of your forward and reverse reactions. So it's a pretty beautiful thing, I think.
So just to restate this concept, because this is really just a beautiful linkage between the study of kinetics and the study of equilibria that we've already completed. For any reaction, A yields B that's at equilibrium, you have no change in the net reaction rates of the system. So this must mean that the forward mass action expression must equal the reverse mass action expression. So you can just rearrange this, and you get K forward over K reverse must equal the concentration of B at equilibrium divided by the concentration of A at equilibrium. And of course, this B divided by A is also your big K, your equilibrium constant for this reaction. So this is just a simple toy model that I prepared to demonstrate this concept to you. And you can see here we have a system where A can produce B reversibly with a forward reaction constant of 0.01 and a reverse reaction constant of 0.05. And I've started off this system at time 0 with an initial concentration of A at 1 and B at 0. And so you can see as the reaction begins, the reaction rate in the forward direction is very high because A is producing B and there's a lot of A in the system. And the reaction rate in the reverse direction is 0 because there's no B to be transformed into A reversibly. But as the concentration of A decreases in the system as the time evolves, and the concentration of B increases in the system, you can see that these reaction rates come together, the forward reaction decreases and the speed of the reverse reaction increases until they equal each other. And this is the state of equilibrium in the system. Now look over here, look at the concentrations that you see arising at equilibrium. So you go out to the end of this reaction. What are the concentrations here? You have the concentration of B being 2/3, or 0.6666, and the concentration of A being 1/3. Now, just put this into your equilibrium reaction quotient, B over A, with respect to the forward direction of the reaction, and this equals 2 over 1, or 0.666 divided by 0.33, which you'll also see 2 over 1 equals your the quotient of the reaction Ks. So 0.1 divided by 0.5 is a 2-to-1 ratio. Or 0.01 divided by 0.05 is a 2-to-1 ratio. So you can see here how you have the equilibrium reaction rates yielding your equilibrium concentrations. Okay, that's all I have for you today. Today we learned how to write an expression for the instantaneous rate of a chemical reaction based on the concentrations of the reactants that exist in that chemical system. And this is simply the law of mass action. But how can we take this instantaneous rate and determine, say, if I have 10 units of A at time 0, what my concentration will be at time 10 or time 20? How do we use that instantaneous rate to determine the total change over a finite amount of time? That's going to be the subject of these next videos when we integrate these differential equations that we've developed to define changes in chemical systems over finite differences in time. So I'll see you then.